All right. How you guys doing? Seem a little lively today. Doing all right? Happy the weather's turning? Although it was still a little warm, I guess, last night and this morning. All right. Go ahead and grab this if you haven't. And we're going to get started back with granular filtration. We'll do, it's pretty simple, so we're not going to do anything crazy complex today. Then we'll solve a problem, and we might end up with a bit of time to begin membrane filtration. If you notice on Moodle, I've updated a couple things. Planning to go through the exams with you at some point next week. I began grading them, and I'll talk more about that when we go through them. But I've activated the third homework, just like the others. You know, it's will be graded for completion. I believe most, if not all, of your homeworks 1 and 2, my TA has been grading. So if you have any questions about that, you're welcome to contact me. Since it's just completion, my policy is if you did 3 out of the 4 required problems, you're getting 75%, right? And we're just kind of looking for you to have shown that you made an effort and found an answer, right? So that'll be the same for the next homework that's posted. Of course, we're only partway through the materials for that because that homework will cover essentially everything for the second exam. So by the end of today, you should be able to get started on it, but there's, of course, membrane filtration and disinfection topics that you'll still need to address. Okay, so that's the plan. I will also talk at the end of class today about a required reading. It's not too onerous, but I will add a quiz, and that quiz will be added to your total participation grade as a component of it. So there will be a Moodle quiz. I think I've already posted that. You should read the thing first because you'll have 5 minutes during the quiz, so that's not really enough time to grab all the answers from the assigned reading, unless you're a really, really fast reader, in which case I guess you can learn in 5 minutes and be good. But it's a short quiz. It'll be Moodle, and that'll just kind of be automatically graded for you. All right, and I'll show you that at the end of these slides. Okay, so last time we were talking about granular filtration and the different times where we would stop a cycle if we, and I'm just going to kind of repeat this quite a bit, so I apologize if it gets old, but really the most important part of understanding granular filtration is understanding the types of cycles we have to operate on, and therefore how much water we are using or wasting or producing, all of that, okay? So if we started a cycle, we do some rinse, and then we operated for some time and we stopped, and then did kind of backwashing and rinsing, or excuse me, backwashing and maybe air purging. If that's our typical cycle, we said that the turbidity is one way we could monitor it, how many particles are in there, and it would kind of look something like this, where during rinsing, we have a lot, and then we should have pretty clean water, and eventually we're rising, and it's getting dirty again, right? So we talked about that last time. Just a little reminder, this is what we're talking about. And now that we kind of understand how it works, next I want to put some math to it to say, okay, well, how much water did we produce? How can we sketch this up in terms of where's the water going and how much we're producing? So, of course, in order to design a treatment plant of some kind, even if this is just treating your swimming pool's water with a sand filter, which is how, probably the most frequent use of these types of filters is your swimming pool or your neighborhood swimming pool or whatever. There are probably sand filters doing approximately the same thing. So how do we design it? Well, we need to know how much water we have to produce. Almost all of our water needs are some kind of water demand. If we are providing clean water, we have to provide a certain amount per time because that's how much this community, this city, village, whatever, whoever it is, that's how much we have to provide at any given time. So we can't say, all right, well, just pause on drinking that water or showering for a few minutes while we take this filter offline. That's a no-go, right? We can't do that. So we have to design on a net water produced per time type of a situation. So how much water can be produced as a net amount, and this is going to be I say amount, but kind of a flow rate, right? We need a certain amount of water per time that must be met. Now, if we think about one filter, when it's operating, one granular filter, while it's operating, it's produced to stop it. Then we have to consume some of the water we produced. So in total, this one filter is going to essentially give us a scenario that it's going to produce more than enough on average during filtration, and then it's going to consume some so that on average it's producing a certain amount. And that's what we kind of have to care about, is how much water on average is this filter producing if we average over multiple cycles, or the total cycle as a whole. All right, so then we're going to have a few more language or terminology pieces that we have to get right. Otherwise, you just get the problem wrong. So that would be the production rates are different from the effective production rates. So if we have a loading rate or a production rate, I'm saying those two are going to be the same thing. So we'll say a loading rate. It's the same thing as saying a production rate, because what I'm talking about is at what rate are we loading water onto this filter. Like we talked about last time, as we're piling more water onto the filter, gravity's pushing it faster and faster through to achieve a net loading rate or net production rate that's equal to the rate at which we're adding the water. Okay, so we're loading the water onto the filter. It's one way to load a step. That is during this moment. Yeah.
So that's like the second that it touches the granular membrane to the second that it leaves the granular membrane?
This is just during the time that we are producing water. I don't quite understand your question. We're not looking at any time frame about the water passing through the filter necessarily. We're just talking about during the time, during the 24 hours or whatever, that we are producing clean water. That's the rate at which we're doing that is the production rate. Okay? And we're going to distinguish this because we're going to have an effective loading rate that we'll talk about in a few minutes, where we have averaged over the cycle time and accounted for all the water that goes to waste. So that's going to be the distinction here. Is one is describing during production, during the filtration itself. That's our loading rate or production rate. Now we can have an equation for this here. We'll say VA, our production rate, is going to be the amount of volume that we're adding per time divided by the area through which it's going. So the filter is going to have some area, and it's going to be water going through that area per time. So this is going to be not actually a flow rate directly that we're talking about here. We do need to find a flow rate, a total flow rate, but the reason we're going to hone in on this loading rate as looks like a velocity, also known as a flux, because it's an amount of water passing through some area, gives us meters per time, as we'll see in a second. The reason we're going to do that is because then we can account for, what if we have 8 filters? What if we change that to 10 filters? What if we take 3 of them offline? That's going to change our area, and that's then going to give us a way to handle our flow rate given some filter area. So this loading rate is going to be the flow rate over the area, and our units here then would be something like cubic meters per second per square meter. Of course, maybe we do gallons per minute or gallons per second per square foot. Maybe that's going to be more commonly done. Doesn't really matter as long as we're keeping our units in line. So a couple typical production rates for a rapid sand filter in one of these bed type filters. These would tend to be a little higher in one of the packed columns that can support a little higher pressure. But in a typical system, we might get anywhere from 5 to 25 liters per square meter per second, or that would translate to 2 to 10 gallons per minute per square foot. Okay, so you can stop and think about that. Okay, how many gallons do I have to pour into some area in 1 minute? Okay, I can do 2 gallons in this area. That's how much water we're producing, right? That, you can kind of conceptually see that if you stop and think about it. So it's a reasonable amount of water loading through there. It's not crazy fast, not crazy slow. That's just kind of a typical range. Okay, so then our Q here, of course, is our flow rate, but here we're specifically describing the flow rate through the filter. So in this equation, this Q will be flowing through the filter. We need to keep that in mind because we're going to solve for a net Q for the entire plant. Almost every problem in some way is going to be related to how much water are we producing for the entire plant, and also, by the way, how much water is passing through this filter. Both of those terms are going to be relevant, so make sure that when you're doing a granular filtration problem, in some way, you're distinguishing between the Q that's relevant to the one filter versus the Q that we might need for the entire plant. Okay? So it's at its base, it's very simple, but there's enough small details to keep track that it's easy to make some mistakes here. Okay, so we have this loading rate. If we look at this cubic meters per second per square meter, this will end up just being meters per second. So it's essentially velocity that's going through the filter. The velocity at which water is passing through is our loading rate during production. Therefore, we could have a backwashing rate where we're doing the backwards, and that would be just the same type of situation going the other direction. We could have a rinsing rate, but if we're rinsing the filter, we're going to do that in the same way that we are going to produce water with the filter. So we'll talk about each piece of the puzzle here, but you can consider the fact that you could have a different rinsing rate. We're not going to, but you could. You could have a different backwashing rate, which we will often have, a little faster backwashing, flush it out a little more vigorously, make the process take a little shorter time so we can get back to producing water. So just a few notes there, and overall this concept here is essentially a flux, a flow rate per area. We're going to see this quite a lot more during membrane filtration as well. Okay, is this making sense so far? Yeah, question.
So,
he knows he's the only one. It was funny because you didn't even look at me. You knew you were the only one with the question.
the production rate, so these are in terms of like a flow over time per meter squared, but you had derived it as just meter or just length over time. So which unit?
So if we take a flow rate, right, so a volume per time, and then send that across some area, your units with a dimension cubed for the volume divided by the area that you're passing it through is going to be dimension squared. We'll end up with just one, like the length dimension to the 1 power divided by the time.
Okay. Oh,
So that's what. So if we take the meters here, we'll end up with the meters per second, right?
Right. And so in terms of like gallons per minute per feet squared, those gallons and feet squared can't cancel. So
Right. You'd have to convert how many cubic feet are in 1 gallon. Yeah. So maybe on a homework or something, I might have you do that. On an exam, unless I explicitly give you the gallons and feet conversion, I wouldn't expect you to do that, right? A lot of times I try to just work with metrics, or if I'm not, I've already told you the expectations of what unit conversions I expect you to know. I would give you a table or a conversion factor if I wanted you to convert that one. But yeah, it was a good question there. The units are a little funny when we do gallons per minute instead of cubic feet per minute per square foot. All right, So there's a couple of numbers that we want to know about when it comes to operating these filters. I've already talked about that effective loading rate. Essentially, we want to know how much water are we producing over time on average. I'm actually going to start with a different but somewhat related metric, which would be how efficient is the filter and the cycle given or on a water basis. How much water are we actually producing compared to how much we're using to make clean water? So if we take 100 cubic meters of water, how many of those are we getting out as clean water? So a filter efficiency then will give us that percentage. So if we have a filter efficiency of 95%, then we get 95 cubic meters of water when we wasted 5 cubic meters of water for the backwash and the rinse. So to get there, it's pretty simple. We're going to say this new Greek N, I guess, letter. We'll do this on a volume basis. So it'll be the volume filtered minus the volume that we use for backwashing minus the volume we use for the rinsing divided by the volume filtered. So the volume filtered will be the total water that came in during that filtration, right? So VF, this will be during filtration. If we have some air purge, there's no water happening there. And then backwash would be here. And then rinse will be here. So if we take a look at it this way, our backwash here, that's going to be our VB. Our rinse water, that will be VR. And so what we're doing is we're taking the total amount we produced, VF, minus the amount of water that we use during backwash. So we take some of the water that we produced, and we'll subtract the amount that we're rinsing from it as well, and divide all that by the total amount we produced. So that'll give us some filter efficiency term. Then the real question then becomes, well, how do we solve for each of the volumes? One thing we can say is if this would give us a ratio, you could multiply it by 100% to get to percentage efficiency, right? That's kind of optional. So how do we find a volume? Well, we have this water flowing across the filter. We're going to need to know how much area the filter occupies, right? Because it would be a lot different if my filter was the size of my water bottle in terms of the surface area there compared to the size of this classroom, right? This classroom would be a little closer to the size of a typical filter in some municipal treatment plant, whereas, maybe you have a couple columns or, a filter with this size of a area might be able to treat an aquarium or something, right? 100-gallon, 200-gallon aquarium. Okay, so you kind of get the picture here of, well, we need the area, and the way that will work is we can take the area and multiply it by the loading rate. That'll get us back to cubic meters or volume per time. So we have the loading rate is a per time. The area times that distance per time will give us a volume per time. Then we just need to know how much time. Get rid of the time factor, then we've got volume. So these equations, I don't think I did update the formula table, but I don't think these are on the formula table because they're that intuitive. Okay? You should be able to know how to get your volume given that you have this kind of flux situation. If you really wanted to, and I have a question. Sorry, let me address that. So if you didn't see the attendance, you can try rewinding to the beginning of the session, or I'll pull it up here for a second for you. And let me know if that doesn't work rewinding. Okay, so if we just define this in terms of flux, which we will take a look at flux primarily in the membrane section, but we often define flux as Q over A. We could rearrange this and say Q is equal to then the flux times the area. The flux is essentially our loading rate. So if Q is then VA times the area, well, if we want to change from Q to volume, we have to multiply it by time, right? As Q is volume per time. So if we continue this here, we would say volume per time equals VA times A. Multiply both sides by the time, and you get our little equations over here. You'll see that we have some subscripts for each component because during filtration, we have a loading rate. During rinsing, we are using that same loading rate. During the backwash, we are going to use a different loading rate. If you're given no information, you could assume that it's the same, but oftentimes we'll use something a little faster. So if there's absolutely no info about the backwashing rate or backwashing loading rate, then we can assume we're just going to use the loading rate value. Usually I'll try to give you I'll try to specify, maybe I'll say it's twice the loading rate or something. So you need to pay attention to it, as it very well could be a different one. So we're going to use essentially the time for each piece. So we might have some time for filtration, time for air purge, time for backwashing, and a time for rinsing. And now you can see we can find the volume in each case given those parameters. The area of one filter is going to be the area of one filter. That'll probably be in the problem somewhere. Maybe we're trying to solve for that. But here's, the area of the filter will remain constant across these three pieces. The loading rate VA, maybe you're solving for that, maybe you're given that. But that'll be the same for the rinsing and the production. So rinsing and filtration, and I say filtration, we could also call that production. And of course, each component has some time. So now, hopefully you're having a little better of a feel for why I keep drawing up this silly little timeline over and over again, because I really want you to know where are the pieces and why are they there, how long they might take. Have all that in mind so you can piece this together. Once we solve for these volumes, the filter efficiency is quite simple, right? So that part is quite simple. You'll have this on your formula sheet. It's just a matter of interpreting and understanding what you need to do with the pieces. Okay. Now we get to the other piece to say, well, what is our effective loading rate? This is actually going to be a little different than just simply taking that efficiency and multiplying it by our loading rate. You'd think maybe you could do that, but it doesn't account for the differences with the air purge. Or really, it also doesn't do a good job accounting for the time that you might be operating on the backwash that's at a different rate and all that. So the effective loading rate, it'll be close to that efficiency times the normal loading rate. So you could double check that, but it is a different formula. It does come out to have different numbers. What we can say is, let's take a look at essentially what is the each volume per area. So each amount of water that has passed through for each step, for the filtration minus the backwash minus the rinse, divided by the total cycle time. a simple way to say that would be to say the volume filtered minus the volume backwashed minus the volume rinsed. And take all of that and divide it by the area of the filter, and you see that's in the denominator in each component here, so we just brought that to the bottom. So we'll have the volume filtered minus the volume backwashed minus the volume rinsed divided by the area of the filter times the cycle time. So you'll be given this formula in the formula sheet, so you'll have that as well. This is that effective loading rate, meaning this is on average. So if our loading rate is here for the filtration time, then across the entire thing, we have our effective loading rate, REF. So, should the effective loading rate be larger, smaller, or the same as the loading rate? Smaller? Anybody agree? Anybody disagree? Anybody awake? Okay, yeah. And smaller is correct because we have to consume some of the water, we have to stop for some time. So the effective on average, we will always have a slower effective loading rate than the actual loading rate during filtration. So we can just keep in mind that it won't be a whole lot smaller, we hope, if it's a good filter, but it will always be less than. In fact, like I said, it should be similar to taking the efficiency and multiplying it by that loading rate. It'll be in the same ballpark. Not exactly the same, so don't do that, but it'll be similar. All right, does that make sense? Okay, yes. And like I've said, this is important to get this right. It's takes a little time to let it sink in. So a lot of small pieces, but at the end of the day, it's going to be nice and simple. So the effective loading rate is just basically saying, for this filter, if I just pay attention to how much water is flowing across it during its entire lifetime, let's say 2 years, on average, how much water is it producing? Okay, per area, if we take the water production per area over a very long time, including all the stops, all the backwash, all that, that's our effective. Okay, we can actually do that with just one cycle time. We can calculate all of that with just one cycle time, assuming that's same cycles repeated over and over again. So we're just taking one cycle time and calculating the average that way. But this is the effective, in reality, accounting for all the downtime. Okay, so this is the piece that's very convenient, very necessary in order to calculate, how many filters do we need for the entire treatment plant? Because we need some filter area times this number to accommodate the entire treatment plant. Okay, then if we have some area per filter, maybe we can find the number of filters. All right? Yeah.
So essentially, like the reference rate, or the effective rate, considers how VB, the rate of backwash, takes away from the rate of production.
Exactly, and where it's doing that is right here. So we take the volume filtered minus the volume rinsed, minus the volume used in the backwash, minus the volume rinsed. That has to go to waste, and accounts for it there. All right, make sense? So let's do a problem then, and we're basically done with granular filtration. All right, so we have here a conventional water treatment plant, treats 2.4 cubic meters per second of river water The filters of the plant are 8 by 8 meters surface area, and they operate on the following schedule. The filter is cleaned once in each 24-hour period. The backwash rate is 10 liters per square meter per second, and that's done for a period of 8 minutes. It takes an additional 8 minutes to drain the filter, break up the media with air injection, and of the total filter cycle time of 24 hours, 15 minutes is used for rinsing of the filter after backwashing. During production, water is applied to the filter at a rate of 5.5 liters per square meter per second. So you can see here a lot of different pieces, a lot of different bits of information with the language that we've been using. Once we get it all in place, we should be able to solve the problem. So A, what is the filter efficiency? I'll rewrite these equations here for you. And B, what is the minimum number of filters required by the plant? So feel free to work together, feel free to work alone, but work on this, feel free to ask me questions, and see what you think.
Where'd you get the time for the filter, the 84.5 seconds?
So as you probably noticed, so you're not given an amount of time for the filtration, but you're given everything you need to know to solve for it. Right. So you're given the total cycle time, it's 24 hours, right? So you just have to subtract the other pieces. So if you get stuck on that kind of thing, just remember how many times I obnoxiously drew that timeline. So that's probably one of the first sticking points for this problem, solving for that. I went ahead and put it in seconds. You can do what you like there. I'm going to check in with you here. How many of you are done with part A and you're moving on? Okay, how many of you still working on A? Okay, I'm going to leave this up here and let you continue working on it for a couple of moments. I'll get a question in a second. And then I'll talk you through this, make sure you're there, and then I'll give you a little more time for B. A question?
Efficiency is divided by VF, right? Or
Yeah.
Or total volume.
Yeah, it's divided by VF, which is kind of the total volume.
What is the efficiency with respect to the volume
With respect to the volume that we filtered, yeah, during production.
there was 23.483 hours that it was in production, and so I used VA, converted that to meters, seconds, minutes, multiplied that by the area, right? And I got this.
Yep.
But I'm confused why the total volume is less than the volume of the filtration.
We're not calculating a total volume in any spot.
So what is VT?
It's a VF that looked like a VT. Where do you see it?
Here.
Yeah, it's definitely a VF that looks like a VT. That's just my bad handwriting.
So maybe
Okay, so
rounded differently?
yeah.
So then using that and using the total time, and divide that out, solve for A F, and I got 60.5 meters squared, which should just be one filter.
We'll come back to that part, but this you got that correct. So I'm going to do B with you guys in a moment.
Okay.
So we'll come back to that. All right. So I'm going to walk through part A, make sure we're on the same page on that. And I had a good clarification here. One part being that my handwriting is not the best, so this should be VF here, not a VT. And by the way, one thing to consider for this filter efficiency is when we are rinsing the filter, you could probably take your river water or whatever source and take that and use it. But I think it's going to be more common perhaps, or at least this formula seems to be taking cleaned water that was already filtered in the last cycle or is being filtered by some other filter and getting calculated into here as if we had already purified that water. So it's taking away from the total water that we took in from the river and subtracting that because we're sending it back through to rinse and it's going to waste. So essentially what we're doing is we're taking the total amount of water that we took from the river minus the water we sent to waste, dividing that by the total amount of water we took from the river. So that's probably the best way to think about it. That might clarify a little bit this question here about what was V total, why is this not adding up? If we consider it in that manner, which I think is a little different than how I explained it last time, that should make sense. Maybe in practice, maybe you could use just river water and just begin your filtration and send it to waste. But at least this equation, the way we're calculating it here, that's probably the best way to think about it. Take clean water to rinse our filters, and then we begin. Okay, at any rate, that's the equation. Here's the process. So hopefully by now you've had a chance to check. I think the tricky parts, A, would be recognizing that you're given several times, but you're not given how much time is actually filtration time. So it's just up to you to draw the little timeline and recognize, okay, I have these pieces, I have the total, and process of elimination kind of thing. We can get a filtration cycle time. You could convert your filtration rates into minutes or hours or days, whatever you like. I left it in seconds and then converted my times into seconds. So do as you see fit. That's just happened to be what I did. So I ended up with 15 minutes for the rinsing, 8 for backwashing. That's all given. We were given a backwashing rate different than the loading rate. And then when we set up each piece here, the volume filtered is going to be essentially that loading rate times the filtration, filter area times time for the filtration. The only difference, so rinsing would be the same setup, it's just smaller time. And then backwashing will be the same setup except using the backwashing time and the backwashing loading rate. So if you do all that, you should get these volumes. If you get these volumes, then you should get this filter efficiency putting it into the numbers, right? So then we have part B. What is the minimum number of filters required by the plant? So now we're trying to meet that Q total of 2.40 cubic meters per second. Have you guys already attempted this, or would you, or okay, let me ask a better question. Would you like a few more minutes to attempt this part now that you got that? Yeah? Okay. So maybe I'll set up just a tiny bit of it, and I'll just go ahead and say, have at it.
So you have the flow rate that's like going into the plant, right?
Yeah.
And so my approach was that I was going to use the effective rate over the entire cycle, right? To
Yeah.
find a new velocity, so to speak, right?
Yeah.
And so we can take the flow rate that's going into the plant, divide that by the reference or by the effective
Loading rate.
effective loading rate. And you should get an area, and then divide that area by the filter area and get how many filters you're going to have, which is like 7.
Sounds like a pretty good approach to me.
Not right.
Do you want the suspense? No, I think that sounds right.
Yeah. What was the answer?
I'll figure it out when I get there.
Oh, okay. Yeah. Okay.
I mean, take a look. I'll show you.
Oh, okay.
It's like literally here, and okay.
Oh.
But there is a little surprise there.
Uh-oh. All right, we'll see.
All right, I'm going to give you 2 more minutes, but I'll let you know right now if you did not use this equation, then you're doing it wrong. Said if you did not use this equation, then you're doing it wrong. So give it a couple minutes to double check or finish up or whatever you like. All right, so how many filters do we need? I hear 7, I hear 8. No, okay, I see, I'm hearing and seeing some numbers. Not 7.11? But what is the correct answer? Okay, good. So some of you are catching on to the trick here. If each filter is 64 square meters, do you expect an operator to install or somebody to install 0.1 filters? No. Will the 7 filters do the job? Also no, right? Because we needed more than 7. And since we can't round down, we can't use exact, we have to round up. So it's a little bit of a strange case, but if you do the calculation, yeah, this should become about 7.11, I think. But we have to round up because 7 filters will not satisfy the condition. Okay? So small little trick at the end there. I wouldn't count off a ton for you to miss that, but it would be technically wrong to round that down. Okay? All right, does this process make sense? And by the way, I didn't walk you through exactly. I left it here on the board, but we can kind of look at it. With the lens of, well, on average, how much flow are we producing from one filter? And that's why we need this R effective. We just multiply the R effective by the area of the one filter to make like a Q effective for one filter. And then we take the total flow rate that we need and divide it there, and there we have it. One thing you'll notice is this gives us a little bit of buffer room. If we do design it this way, we have a little extra capacity. So maybe we have a little extra time to deal with, or our water supply could grow a little bit with these filters. So this design here is for the scenario where we are doing routine maintenance. Probably in practice, we would build or design a plant to have some capacity in case we need to do longer term maintenance on something and have a filter down for a month, right? Something like that would probably be built in addition, but we're not going to trouble ourselves with that. We'll just stick with, okay, for this specific operation here. Okay, any questions or issues? Okay, so I think this gives you plenty of appreciation for this flavor of problems. It's not exactly mass balance, but it's still kind of materials balance sort of a deal. You'll find this and membrane filtration are kind of similar in that manner. We need to know the context. We need to be able to navigate the terminology in order to smartly design some filter for the treatment. Okay, this brings me to your reading assignment. There was a very large outbreak back in, this paper is 93, but I think the outbreak was 89 perhaps. And this was in Milwaukee. There was a very large cryptosporidium outbreak. Did have something to do with the filters. So this entire section 2, I guess, of our course, the exam 2, is kind of related to this. So as you go through the next few lectures, this material might be kind of interesting. Or at least you're going to have to take a look at it to try to do well on that little quiz. But essentially, you'll find out that cryptosporidium, it's a stomach pathogen. For most people, it's just, you'd think of it as hiker's diarrhea. It's something you might contract if you drank water that was not really too safe, or you did a poor job disinfecting it. Some resistant organisms have these cysts. Doesn't take many of them to give you an infection, and then it stays for a long time because it takes a while for your body to get rid of it. So that's sort of the thing. Now, it's a big problem for people that are immunocompromised. It's very difficult for somebody with a compromised immune system to deal with it. So it actually caused many deaths for that type of situation. So take a look at that. You'll see on our Moodle page, I have the reading looks like this. It's not super long, but it is kind of a science article, technical article. So what I do not recommend is you try to read every last word and understand every last word. That's not the way to go, okay? I know that might sound funny. I'm giving you a reading assignment telling you not to read the whole thing. But really, when you want to learn something from a science article like this, journal article, you probably want to do a couple things. One is read the abstract. Make sense of most of it. Get the picture of what's going on. Then take a look at the introduction segment. This will give you the context of what's going on, what's happening. The last paragraph in any intro is probably going to tell you exactly what they did to study. So that's a great one to focus in on. the methods are probably going to go over our heads, even mine in some cases. So maybe glance at them and see, oh, okay, they did clinical stuff, they did ice during the outbreak. I guess they preserved some samples, surveillance stuff, the infections. Okay, skipping along, results. Okay, for results, maybe the first thing you ought to do is take a look at the graphs. Try to make sense of some of the graphs. And just save yourself a little time from trying to understand every last word. Once you find something that makes you curious, go and read a little more. So if you see like this plot, it's like, oh, cool. This is tracking maximal turbidity. Hey, we talked about that in class, right? Maybe I should read what they're talking about with figure 1. Okay, here's figure 1, something. Maybe I'll read a couple sentences there to try to understand what's going on. This is a better way than trying to just read straight through. Find a section that you decide, hey, I think I'm learning something there. Let me read straight through that section. Okay? And then, of course, eventually go on and get to the end where they have some conclusions and say, okay, I'm going to pay attention and see what did they really say that they learned here. I guess they don't really have a direct conclusion, but they're going to conclude in some manner. So take the last real paragraph of the paper and focus some attention there to see like what are they really caring about in this paper. So read as much as you feel like you need to learn something, and excel on that quiz. All right. Feel free to bring me questions about it or anything. We'll do membrane filtration next time. So we'll see you Tuesday.